Hello, everyone. Thank you for coming today. It's a pleasure for our company to present our latest solution to you. Today, I will introduce the content related to I/O. Today's introduction mainly includes two topics. First, a general introduction will be given. Next, a brief introduction will be given to each peripheral module. This report is mainly introductory content. For the technical details, you can learn more about them through the SDK online documentation. First, a general introduction. First, let's introduce the I/O demo project. I/O demo project shows how to use peripherals to communicate with other devices. A specific peripheral and its usage scenario can be changed to demonstrate, with its source files added to the build target and its demo functions called in main function. The I/O demo supports the RTL87X3E, RTL87X3D, and RTL87X3EP development kits. To quickly build a development environment, please refer to the SDK online documentation. The following is an introduction to the compilation and download methods of I/O demo. Taking the I/O demo of RTL87X3E as an example. First, open the I/O demo project file of RTL87X3E, then select and compile the corresponding target. When the compilation is successful, the app bin file will be generated. Download the app bin and resource bin to the EVB board, and finally press the reset button, and the I/O demo application will start running. For detailed steps, please refer to the SDK online documentation. The I/O demo project is located in the board EVB I/O demo directory. The application source code is located in the SRC sample I/O demo directory. The structure of the I/O demo project is shown in the figure. When the application is powered on or the chip is reset, the main function will be called. The GPIO int demo function can be replaced by the demo entry function in the demo files, such as ADC demo function in the ADC demo source file. Note that each demo entry function is independent of each other. The initialization of peripherals is mainly divided into 4 steps. First, set the peripheral's PINMUX and PAD. Next, enable the peripheral's clock signal. Then, set the peripheral's initialization parameters. Finally, enable the peripheral. The description of each peripheral name is shown in the table. The demos of peripherals are described in detail in the SDK online documentation. Taking I2C as an example, the specific contents of the demo code support list are introduced. The first line of the list describes the name of the demo code source file. The line sample purpose introduces the main purpose of the sample code. The line brief introduction introduces the main content of the sample code. The line file path introduces the path of the sample code in the SDK package. The line function entry introduces the entry function name of the sample code. The line hardware connection introduces the hardware connection part of the sample code. The middle lines introduce the parameters of the peripherals set in the sample code. Expected result introduces the expected result after the sample code is executed. Next, we will introduce PINMUX and PAD. PINMUX is an abbreviation for pin multiplexing. Because the SoC has a limited number of pins, pin multiplexing allows the SoC to use the limited pins for various functions, such as SPI, I2C, and GPIO. PAD is used to control the behavior of a pin, such as pull-up or pull-down, output high or low level, and wake-up functions. As shown in the figure. The PINMUX circuit and I/O modules are in the core domain and will be powered down during low power mode, so they cannot work during low power mode. The pad circuit is in the AON domain and will not be powered down during low power mode, so the pad can work normally during low power mode. The pad is mainly used to maintain the pin output state or wake up the system in low power mode. The pad can be configured as PINMUX mode and software mode. Only when the pad is set to PINMUX mode can this pin be connected to the core domain to achieve pin multiplexing. Configure PINMUX status of the pin by calling function PINMUXConfig. Configure the pad status of the pin by calling function PADConfig. The table lists the demo codes supported by PINMUX and PAD. For detailed information, please refer to the PINMUX and PAD section of the SDK online documentation. Next, we will introduce GPIO. GPIO is programmable general-purpose input-output. Each GPIO pin can be configured by software as an output, input, or interrupt peripheral function. GPIO supports three modes: input, output, and interrupt. Input mode is used to detect GPIO input signals. Output mode is used to output high and low levels. Interrupt mode is used to detect level changes of input signals. The initialization process of GPIO is shown in the figure. First, call the function HAL GPIO init to enable the clock signal of GPIO, then call the function HAL GPIO init pin to initialize the specified pin as GPIO function. If you want to use interrupt mode, first call the function HAL GPIO init to initialize the interrupt mode. Call the function HAL GPIO set debounce time to set the hardware debounce time. Then call the function HAL GPIO setup IRQ to set the parameters of the interrupt mode. Then call the function HAL GPIO register ISR callback to register the callback function. And finally call the function HAL GPIO IRQ enable to enable the interrupt. The table lists the demo codes supported by GPIO. For detailed information, please refer to the GPIO section of the SDK online documentation. Next, we will introduce timer and PWM. The timer consists of a 32-bit automatic load counter. Each timer is completely independent and does not share any resources. They can operate synchronously together. The timer can operate in two modes: user-defined count mode and free-running mode. In user-defined count mode, the timer counts down from the value set by the user. In free-running mode, the timer counts down from the maximum value. When the timer counter is enabled after being reset or disabled, the timer counts down from its initial value, and when it reaches 0, an interrupt is triggered. This section introduces the basic operation flow of timer. First, call the function HWTimer create to create a timer, then call the function HWTimer start to start the timer. When the timer counts to 0, the callback function registered when the timer is created will be executed. This section introduces the basic operation flow of PWM. First, call the function PWM create to create a PWM, then call the function PWM pin config to configure the pin used by PWM, and finally call the function PWM start to start PWM. The table lists the demo codes supported by timer and PWM. For detailed information, please refer to the timer and PWM section of the SDK online documentation. Next, we will introduce UART. UART provides a flexible method for full duplex data exchange with external devices. The UART utilizes a fractional baud rate generator to provide a wide range of baud rate options. It supports half-duplex single-wire communication. UART can also be used with GDMA to achieve high-speed data communication. The initialization process of UART is shown in the figure. The first step is to turn on the clock signal of UART. The second step is to set the baud rate of UART. The third step is to set the checksum, stop bit, and data bit of UART. The fourth step is to set hardware flow control. The fifth step is to set the level of UART interrupt trigger. The sixth step is to initialize UART peripherals according to the UART parameters set above. The seventh step is to configure the interrupts of UART. The table lists the demo codes supported by UART. For detailed information, please refer to the UART section of the SDK online documentation. Next, we will introduce GDMA. GDMA is used to provide high-speed data transfer between peripherals and memory or between memory and memory. The data transfer can be done independently of the CPU to reduce the CPU overhead. Each channel of the GDMA controller can handle requests from one or more peripherals for memory access. The GDMA controller has an arbitrator to coordinate the priority of each GDMA request. The initialization process of GDMA is shown in the figure. The first step is to enable the clock signal of GDMA. The second step is to request an unused GDMA channel. The third step is to set the parameters of GDMA. The fourth step is to initialize GDMA based on the set parameters. The fifth step is to configure the interrupts of GDMA. The table lists the demo codes supported by GDMA. For detailed information, please refer to the GDMA section of the SDK online documentation. Next, we will introduce I2C. The I2C bus is a two-wire serial interface, consisting of a serial data line and a serial clock. These wires carry information between the devices connected to the bus. Each device is recognized by a unique address and can operate as either a transmitter or receiver, depending on the function of the device. Devices can also be considered masters or slaves when performing data transfers. A master is a device that initiates a data transfer on the bus and generates the clock signals to permit that transfer. At that time, any device addressed is considered a slave. The initialization process of I2C master mode is shown in the figure. The first step is to set PINMUX and PAD, the second step is to enable the I2C clock signal, the third step is to set the I2C transmission rate, the fourth step is to set the I2C transmission mode to the master mode, the fifth step is to set the address mode of the slave device to communicate with the master, the sixth step is to set the address of the slave device to communicate with the master, the seventh step is to initialize I2C according to the set parameters, and the eighth step is to enable I2C. The initialization process of I2C slave mode is shown in the figure. The first step is to set PINMUX and PAD, the second step is to enable the I2C clock signal, the third step is to set the I2C transmission mode to slave mode, the fourth step is to set the slave address mode, the fifth step is to set the slave address, the sixth step is to set the AC mode, the seventh step is to initialize I2C according to the set parameters, the eighth step is to configure the I2C interrupt, and the ninth step is to enable I2C. The table lists the demo codes supported by I2C. For detailed information, please refer to the I2C section of the SDK online documentation. Next, we will introduce SPI. SPI allows the chip to communicate with external devices in half/full duplex, synchronous, and serial modes. SPI supports master mode and slave mode. It supports 4 transfer modes: full duplex, TX only, RX only, and EEPROM. The initialization process of SPI is shown in the figure. The first step is to set PINMUX and PAD. The second step is to enable the clock signal of SPI. The third step is to set the transmission mode of SPI. The fourth step is to set the working mode of SPI to master mode or slave mode. The fifth step is to set the data frame format of SPI. The sixth step is to set the clock polarity of SPI. The seventh step is to set the clock phase of SPI. Next, if SPI is set to master mode, set the speed of SPI. Then, select which serial protocol to use to transmit data. Then, initialize SPI according to the set parameters. Finally, enable SPI. SPI slave does not support TX FIFO underflow conditions. The TX FIFO needs to be filled with data before the SPI master starts the transfer. There are 2 methods to avoid this condition. The first way is to send data to the SPI slave TX FIFO before transmission, and then toggle a GPIO to notify the SPI master to send data. The second way is for the SPI slave to use GDMA to send data, that is, enable TX GDMA immediately after the SPI slave is initialized to ensure that there is always data in the SPI slave TX FIFO. The table lists the demo codes supported by SPI. This is a continuation of the table on the previous page, which also lists the demo codes supported by SPI. For detailed information, please refer to the SPI section of the SDK online documentation. Next, we will introduce IR. The infrared module can realize infrared wireless communication with adjacent devices. IR supports configurable carrier frequency, configurable carrier duty cycle, and configurable carrier on/off time. The initialization process of IR is shown in the figure. The first step is to set PAD and PINMUX, the second step is to enable the clock signal of IR, the third step is to set the parameters of IR, the fourth step is to initialize IR according to the set parameters, the fifth step is to configure the interrupt of IR, and finally, enable IR. The table lists the demo codes supported by IR. For more information, please refer to the IR section of the SDK online documentation. Next, we will introduce RTC. RTC is an independent timer. RTC has a set of continuous counting counters to provide a calendar clock. It can be converted into the current time and date of the system by querying the counter value. The initialization process of RTC comparator function is shown in the figure. Firstly, reset the RTC, set the clock division factor of the RTC, set the comparator value of the RTC, then enable the RTC comparator interrupt, and finally enable the RTC. When the RTC count value reaches the set comparator value, the comparator interrupt will be triggered. In the interrupt function, the interrupt status flag needs to be checked first. If the comparator interrupt flag is found to be set, the comparator interrupt status of RTC needs to be cleared. The initialization process of RTC overflow function is shown in the figure. Firstly, reset the RTC, set the clock division factor of the RTC, then enable the RTC overflow interrupt, and finally enable the RTC. When the counter reaches its maximum count value, an overflow interrupt is triggered. In the interrupt function, the interrupt status flag needs to be checked first. If the overflow interrupt flag is set, the RTC's overflow interrupt status needs to be cleared. The initialization flow of the RTC tick function is shown in the figure. First, reset the RTC, set the clock division factor of the RTC, then enable the RTC tick interrupt, and finally enable the RTC. When the counter counts once, it will trigger the tick interrupt. In the interrupt function, the interrupt status flag needs to be checked first. If the tick interrupt flag is set, the tick interrupt status of RTC needs to be cleared. The table lists the demo codes supported by RTC. For detailed information, please refer to the RTC section of the SDK online documentation. Next, we will introduce LPC. LPC can be used for voltage detection and counting. When the LPC detects that the input voltage exceeds the set voltage threshold, the system will trigger the interrupt. LPC can be used to count the number of times the input voltage exceeds the set voltage threshold. When the count value exceeds the set value of the comparator, the interrupt will be triggered. The operation flow of the LPC comparator function is shown in the figure. The first step is to set PINMUX and PAD, the second step is to set the input pin of LPC, the third step is to set the trigger edge, the fourth step is to set the voltage threshold. The fifth step is to initialize LPC according to the set parameters, the sixth step is to reset the LPC counter, the seventh step is to set the comparator value of LPC. The eighth step is to enable the comparator interrupt of LPC, the ninth step is to enable LPC, and finally, enable the LPC counter. The interrupt processing flow of the LPC comparator function is shown in the figure. The first step is to check the interrupt status, the second step is to set the comparator value, and the third step is to clear the interrupt. The table lists the demo codes supported by LPC. For detailed information, please refer to the LPC section of the SDK online documentation. Next, we will introduce 3-wire SPI. 3-wire SPI is used to connect 3-wire SPI interfaces such as SDIO SCLK and has single-wire, single-burst read function. It is also possible to adjust the desired delay timing between read-write. The 3-wire SPI initialization process is shown in the figure. The first step is to set PAD and PINMUX, the second step is to enable the clock signal of 3-wire SPI, the third step is to set the parameters of 3-wire SPI, and the fourth step is to initialize 3-wire SPI according to the set parameters. The operation flow of sending data by 3-wire SPI is shown in the figure. First, check whether 3-wire SPI is in busy state. When 3-wire SPI is in idle state, call function SPI 3-wire start write to write address and data, and then call function SPI 3-wire get flag status to wait for 3-wire SPI to be in idle state. The operation flow of receiving data by 3-wire SPI is shown in the figure. First, check whether 3-wire SPI is in busy state. When 3-wire SPI is in idle state, clear the state of number of read data, set the read address and the number of read data, and then wait for 3-wire SPI to be in idle state and the length of received data to be non-zero, and finally call function SPI 3-wire read BUF to read data. The table lists the demo codes supported by 3-wire SPI. For detailed information, please refer to the 3-wire SPI section of the SDK online documentation. Next, we will introduce CapTouch. Capacitive touch controller uses a single pin and measures the capacitance between the capacitive sensor pin and ground. Capacitive touch controller uses changes in capacitance to detect the presence of a finger on or near a touch surface. The CapTouch initialization handling process is shown in the figure. First, enable the CapTouch function, reset the CapTouch system, then enable the specified channel, enable the CapTouch interrupt, set the scan interval, and finally set the wake-up function. The CapTouch interrupt handling process is shown in the figure. In the CapTouch interrupt function, the first step is to check the interrupt status flag. If the corresponding interrupt flag is set, the corresponding interrupt status needs to be cleared. The table lists the demo codes supported by CapTouch. For detailed information, please refer to the CapTouch section of the SDK online documentation. Next, we will introduce ADC. ADC is used to convert analog signals into digital signals. ADC supports two internal channels, VBAT and VADPIN. It supports two external channel input modes, bypass mode and divide mode. It supports 16 schedule tables. It supports hardware averaging function. Next, we will introduce how to use ADC through ADC Manager. First, if you use an external channel, set PAD. If you use bypass mode, call the function ADC high bypass CMD to enable bypass mode. Then, set the ADC schedule table. Next, call the function ADC MG or register REQ to request a channel of ADC Manager. Finally, call the function ADC-MG or enable REQ to start ADC sampling. When ADC sampling is completed, the callback function registered with ADC Manager will be executed. In the callback function, first read the ADC sampling data, and then get the conversion result. The table lists the demo codes supported by ADC. For detailed information, please refer to the ADC section of the SDK online documentation. Next, we will introduce Sleep LED. Sleep LED is used to control LED to make the effect of blinking light or breathing light. In blink mode, one channel is divided into 3 periods. As shown in the figure, it is executed sequentially from period 0, and after the end of period 2, it goes back to period 0 to continue the loop execution. In breathe mode, one channel is divided into 8 phases. As shown in the figure, it is executed sequentially from phase 0, and after the end of phase 7, it goes to phase 0 to continue the loop execution. The operation flow of the flashing mode of the sleep LED is shown in the figure. The first step is to set the pad, the second step is to reset the sleep LED, the third step is to set the sleep LED to the blink mode, the fourth step is to set the reverse output function, the fifth step is to set the clock division factor. The sixth step is to set the high and low level count values of the 3 periods. The seventh step is to initialize the sleep LED according to the set parameters. And finally, enable the sleep LED. The operation flow of the breathing mode of the sleep LED is shown in the figure. Step 1, set the pad. Step 2, reset the sleep LED. Step 3, set the sleep LED to breathe mode. Step 4, set the reverse output function. Step 5, set the clock division factor. Step 6, set the duty update time. Step 7, set the duration of the whole phase. Step 8, set the initial high-level time. Step 9, set the direction of each duty change. Step 10, set the duty step for duty update. Then initialize the sleep LED according to the set parameters. And finally, enable the sleep LED. The table lists the demo codes supported by Sleep LED. For detailed information, please refer to the Sleep LED section of the SDK online documentation. Next, we will introduce QDEC. As shown in the figure, QDEC is used to detect the motion state of the rotation sensing device. When the rotating device moves, it will output two quadrature signals PHA and PHB. QDEC judges the direction of rotation by detecting the phase change of PHA and PHB. The initialization process of QDEC is shown in the figure. The first step is to set PAD and PINMUX, the second step is to enable the clock signal of QDEC, the third step is to set the parameters of QDEC, the fourth step is to initialize QDEC according to the set parameters, the fifth step is to configure the interrupt of QDEC, and finally, enable QDEC. For more information, please refer to the QDEC section of the SDK online documentation. The interrupt processing flow of QDEC is shown in the figure. The first step is to check the interrupt status, the second step is to mask the interrupt, the third step is to read the direction and counter count value, the fourth step is to clear the interrupt, and the fifth step is to unmask the interrupt. The table lists the demo codes supported by QDEC. For more information, please refer to the QDEC section of the SDK online documentation. Next, we will introduce KeyScan. KeyScan needs to be used with an external key matrix. The function of KeyScan is to efficiently and accurately detect key presses and releases across a matrix of keys. The initialization process of KeyScan is shown in the figure. The first step is to set PAD and PINMUX, the second step is to enable the clock signal of KeyScan, the third step is to set the parameters of KeyScan, the fourth step is to initialize KeyScan according to the set parameters, the fifth step is to configure the interrupt of KeyScan, and finally, enable KeyScan. The table lists the demo codes supported by KeyScan. For more information, please refer to the KeyScan section of the SDK online documentation. Next, we will introduce I2S. I2S interface can support audio protocols such as I2S, left justified, PCM, and TDM. Through the I2S interface, which is able to bridge to an external DSP core, or audio codec audio amplifier. I2S can be operated in GDMA mode or FIFO mode. Set the buffer size according to the amount of transferred data in GDMA mode, or access I2S FIFO directly to transmit and receive data in FIFO mode. It is recommended to transfer the audio data via GDMA automatically since it can reduce the number of interrupts and improve efficiency. The initialization process of I2S is shown in the figure. First, set PAD and PINMUX, then set the parameters of I2S, then initialize I2S according to the set parameters, and finally enable I2S. For more information, refer to the I2S section of the SDK online documentation. Next, we will introduce SDIO. SDIO card is an I/O device that uses the SD bus and SD commands. Support only 2 group pins on EVB to communicate with SD card. Support 1-bit and 4-bit SD bus width. Support optional bus clock, 40 MHz and 80 MHz can only support in RTL87X3D, support multiple block and single block transfer, SDHC max block size is 512 bytes. The high voltage SD card requires an operating voltage of 3.3 V. Support GDMA transfer. Support interrupt control. Next, we will introduce the SDIO initialization process. First, call the function sdconfig_init to configure the SDIO parameters, then call the function sdboard_init to configure PAD and PINMUX, and finally call the function sdcard_init to initialize SDIO. The table lists the demo codes supported by SDIO. For more information, refer to the SDIO section of the SDK online documentation. Next, we will introduce CAN. CAN module is targeted for CAN bus communication according to ISO 11898-1-2015 standard and CAN 2.0 AB. The module also has a part of memory logic for flexible transmission and reception of CAN messages. The logic eases the loading of the CPU and increases efficiency. The initialization process of CAN is shown in the figure. The first step is to set PAD and PINMUX, the second step is to enable the CAN clock signal, the third step is to set the CAN parameters, the fourth step is to initialize CAN according to the set parameters, the fifth step is to enable CAN, the sixth step is to configure the CAN interrupt, and finally, wait for the CAN bus to be in the open state. The table lists the demo codes supported by CAN. For more information, refer to the CAN section of the SDK online documentation.